That's good. Mm-mm. He's all okay. So, right, they're giving us the formula they want us to use. Okay. Read over the question real quick. 1970, U.S. population is 203.3 million. 2007, it had grown to 300.9 million. Assume that population is changing exponentially, which is a pretty big assumption, but we got to make some sort of assumption here. Okay. The first thing they want us to figure out is what's the growth rate of the population. K. Right? So they want us to find this. So if we go up and look at the formula, right, where's K here? So there's K. If our job is to find K, that means that can be the only thing we don't know. That means we have to know what T is, and we have to know what A naught is, and we have to know what A of T is. We have to know all those other values in order for us to find K, because E is a number. E is a number. E is not a variable. Right? We know what E is. It's just a messy number. Right? So we have to know all that other stuff in order to find K. So we need to make sure we can read the problem and find all that stuff, identify all those things. So for part A, what is T? What is A naught? What is A of T? Well, T is time, right? That's pretty simple. Let's say 1970 to 2007. Okay, so there's our time, 37. Somebody grouped me. Yep, good job, Meg. What's A naught stand for, right? A sub 0 means the amount at time 0, the starting amount, the initial amount. So where did this problem start, right? That was our starting population for the data that we have, 203.3 million. And I'm not going to write it as 203.3 million. I'm just going to write it as 203.3, knowing that any answers that come out are going to come out in millions, right? So just keeping that in context. And what's our amount after some time has passed, right? So there's that other population value over there, the 300.9 million. So there's our A of T. Right? So plugging those three things in, I should be able to find K. And this says KT, which would tell me to write, K37. I don't want to write K37. That's a weird way to write a number in a variable. So I'm going to write 37K. Because I know that multiplication can be rewritten in any order that I want, and it's okay. So there's my equation. I can see that K is the only thing I don't know, which means I should be able to solve for K. So here's what we've been working on over the last week. How do we solve this equation? We're done with all the context. Okay. How do we do the math? We need to solve. Can't plug anything in.
Are we trying to get E by itself?
Are we trying to get E by itself? It's a wonderful question, Ruth.
Yeah, I don't know.
Would it be easier if we looked at a simpler version of this problem? Some number equals some number times E to some power? Looks like a pretty familiar equation like we solved on Monday and Tuesday. How do we do this? What's our first step?
Do you divide on both sides?
Divide by
2.
Okay. So what would we do here then, Ruth?
Divide by 203.3 0.3.
So what's hard to see, right? And this is not an uncommon thing, guys. What's hard to see about this is that this right here is multiplication, right? We know in our heads that when I put a number next to a letter that they're multiplying, okay? But what's hard to see is that, is the 37K on the 203.3? Not, right? But when we put them next to each other, it gets really unclear. So if you need to do this for you, if you need to put that little dot there to help you separate those two things, if you need to say that, like visually, that's a lot clearer that the two can get yanked away, then you need to do that for you. A textbook isn't going to do that, though. The textbook is going to write it just like that, where they're just going to smush them next to each other and expect you to pick them apart. Okay? That's what it is. We need to get that E by itself, like Ruth said. We need to isolate that power before we can move on to the next part. So we're going to go ahead and we can throw that 300, that fraction over into your calculator. Okay. So 300.9 divided by 203.3. Okay. And we get this decimal here. Okay. I don't want to write all that down, but I also don't want to not have all that information later when it comes to needing it. Okay. It is a really, really bad idea to round during the middle of a problem. Okay, so I'm going to kind of sit in the middle right now and not write all that down. I'm just going to write down 1.48, but I know that later on I'm going to come back and I make sure I use all those numbers when I go to do some more math. Okay, so I just need to be real clear to myself that while I'm going to round on my paper, I am not going to round in my calculator. Okay. All right, so we've got an E by itself now. And the power by itself. What's next?
Wouldn't you put it into log form?
We would love to put it in log form. What would that look like, Maddie?
ln, and then that long decimal number.
Okay.
Parentheses equal to 37K.
Right. The natural log of 1.48, blah, 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 like Maddie said, equals 37K. What were we after, right? We're trying to solve for K. Well, we can't solve for K when it's up in the exponent spot. Right? What allows us to bring it down is that logarithmic form. Now it's down there at the main level of the math, right? K is in a more recognizable place for us to be solvable. Okay? If you're of the ilk that looking at that 1.48 equals e to the 37K, you don't understand what to do with that, as something as simple as this, guys, I've seen this make a big difference to people. I've seen a lot of students get confused because pretty much every problem we've done up to this point, the power has been on the left side and the constant's been on the right. They have a hard time flipping the numbers around in their head. So if you have a hard time doing it in your head, then write it down. Okay? You know that both sides of the equal side are the same. Those are the same equation. If this is easier for you to solve or rewrite, the purple one's easier for you to rewrite than the black one, then you need to do that for yourself. Okay? The numbers don't care, but if you care, then you need to do that. Just like this. If you need to put that point there because it makes it easier for you to see, then you need to do that. Okay? This is purely like a mental thing. It's easier for you mentally to rewrite that problem this way, then do that. But you guys need to take care of that for yourself. Okay? So just be aware. It's okay to do that. Dang it. Oops, that's not what I wanted to do. Struggle. I think I'm good. No, dear, what did I do? I locked it. Okay. All right, it's all good. Okay. We notice that K is not solved for yet, right? So we still need to get K by itself. We're almost done. And in this moment, right, here's something I want to do for myself. I'd rather have the variable on the left side. And I'm going to push everything else to the right side. Okay. Again, that is purely personal habit. So that's something I do for myself rather than having the K over here. All right. So if you want to do that, you can do that. If you want to rewrite with the K on the right side, you can rewrite the K on the right side. And so now we need to go to our calculator and do that math, right? Except for I said earlier that I wasn't going to accept that rounded decimal for myself. So what I'm actually going to do is I'm going to type this into the calculator. I'm going to show you guys a kind of a simpler way to do that if you've already done the first thing. Okay. So let's all pretend that we had already done the 300.9 divided by 203.3 because we all did it earlier because you're all following along and doing what I asked. Okay. And so I want to take the natural log of that number. So function natural log. And I'll show you guys how to do this on your TIs in a second. So on this app, which is why this app is better than the one that normally comes with your phone. You still haven't downloaded a calculator. All I have to do is go up to that top left thing and just tap that, and it brings it down into my function. So there's the log, and I didn't have to retype it all. More time you spend retyping, the more chances you're going to have to make mistakes. And I wanted to divide by 37, so there's that. There's my k value. They asked us to round that to 3 places. So 0.011 would be the appropriate rounding there, 0.011. So on your TI, how you would do that, and this doesn't matter if you have a TI 80 or a TI 30, it's all the same thing. Okay. So what you do, so if you already had that 300.9 divided by 203 in there from earlier. Okay, so it looks like that. What you're gonna do is hit the natural log button, and you're gonna hit second and the negative button down there on the bottom. So second negative, that's notice it says ANS. That's second answer is what that stands for. So I hit second answer and I close my parentheses. So now it says the natural log of the answer. So what it's done is it's gone up to the last thing and pulled all of those numbers. I don't have to type them all. It pulls them all for me. Okay. And then I want to divide by 37. All right, and there's our 1.011, right? Just like last time. So you can see you get the exact same answer, right? Just as how you do this on a TI. All TIs have that second answer down there on the negative. So you guys can all take advantage of that. Okay? So a couple ways to decrease the amount of typing you do, but keep all those decimals. Okay? Or you need to sit there and type all of that into the calculator. There's our k value. So once we have that k value, all right, let me stop and say, you guys good on finding k? I have no idea why this is here, so I don't know what this is for. Go away. So once we have that k value, we can use that information to write a model equation. Okay? And then we can take that model equation and say, hey, what about 1980? What would the population have been? What about 1990? What about in 2050? Okay? In order to write the model equation, we need two things. We need our initial value and our growth rate. Well, k is our growth rate, and then the 203.3 was our initial value. So here's our model equation, right, for the population change of the United States in the late 20th century, early 21st century. Right? It needs to have a variable in it still, so that we can go and change that and say, yeah, what about in this time? What about this time? And it'll spit out those answers for us. When people are really doing this, the math thing to do is quite a bit more complex because 2 points on a curve is not a good way to define the curve. They would use many, many data points, and then the math for that gets much more complex. It's called exponential regression. It would give you a better k value than the one that we just found from just looking at 2 points. So but it's based around this. So just above our pay grade. But now we can take that modeling equation and use it to answer question C. They said, what year would the population reach 325 million? And so you read the beginning of that question, and that's a time question, right? T is what? Well, if we want to find T, we need to know everything else. So as we look at this, if I want to find that, well, man, E's not a variable, right? E's a number. I know that, I know that. That means I need to know this. I need to know P of T. not P times T, P of T. All right, what's the population supposed to be? Well, that's what they told us. That's the 325 million. So the 325 million is going to go here, and we're going to be able to solve for T. So for part C, all right, so we're going to write 325 equals 203.3 times e to the 0.011 t. And if you look at this equation, guys, it's essentially the same equation we solved for in part A. All right? Some number equals 203 times e to some power. Some number equals 203 times e to some power. Our job was to solve for part of that power, which is what our job was up here. The steps we did here are going to be the exact same steps we do here, just because the numbers are going to be different. That's it. Okay, so we can follow right along with this. So we'll run through that real quick. Divide by the 2, get rid of that coefficient first. So divide by the 203. This time I'm not going to write it as a decimal because I know later I'm going to want it as a fraction anyways, so I'm just going to go and leave it as a fraction. And then this, again, that key step, right, that we rewrite it from an exponential equation to a logarithmic equation. This really is, the most unnatural part of this. So that's the hard, that's the part you guys need to be focusing on the most. That it makes sense to divide by this number, and it makes sense to subtract a number or whatever if it says plus. But this idea of rewriting an equation from one form to the other to solve is a bit more foreign to us. So we need to make sure that we're focusing on that's a big part of this process. So at some point I'm going to have to rewrite it. So you're recognizing it when my power is isolated. That's my rewriting step. And because it's base e, it's natural log. And then the answer, the 325 over 203 becomes the argument. And that equals the exponent. Remember, a logarithm is an exponent. So it should equal the exponent, the 0.011t. Then we're going to divide by 0.011. And that'll give us our t value. So I'm going to go in and type in all that stuff into the calculator. Log of natural log of 325 divided by 203 divided by 0.011. You guys should all be doing this to get that practice done. All you athletes should know how important repeating that motion over and over again is. Just practicing putting your fingers on the calculator, as silly as it seems. It will help you do it better come the test time. So we get 42.6. Let's just go ahead and round to the 10th. It didn't tell us anything. But a 10th of a year, it's pretty good. So 42.6 years, all right? Is that what the question asked us? Not quite. It said which year. All right, it was a time question, but it's not how many years, it's which year. Well, that's 42.6 years from the beginning of the problem. Right? The beginning of the problem was in 1970. So not from 2007, it's from 1970, the beginning. So I'm going to go and add 1970 to that, which would get us to, what, 2012.6? So there's a year, 2012.6. You would never say that to somebody, in 2012.6. This is when that's, right? That's not how we talk. So kind of that ended, how do we end this, right? The beginning of it was all about reading and making sense of things. Well, the end of it should all about speaking or writing and making sense of things. How would you say this to somebody? Your job is to report the population, to somebody, right? How would you communicate that to them, right? I might say somewhere between 2012 and 2013, the population will hit 325 million. About halfway through 2012, population will hit 325 million. There's something indicating that it's, about halfway through the year, a little bit more than halfway through the year. Right? That is not 6 months. 0.6 does not mean 6 months. Okay, but it's more than half of the year. Somewhere in there, that's when the population is going to hit that number, according to our model. Right? So, how do you communicate that? That's how I'm choosing to do it. Okay. I'm gonna give you guys some leeway in there, but I want you guys to be thinking about how should this be communicated. It's a pretty intense problem. A lot to do there. Anything blowing your mind? Anything really confusing you? Okay. Okay. Next one. So the number of new cases of Ebola in the Democratic Republic of Congo has been increasing at a rate of 12.3% each week. If left unchecked, when will the number of new cases double? They're telling us, again, kind of giving us a pretty big hint. Let's use a continuous model. So let's go back and look at those real quick, the continuous models. So we have these two, and I was talking to you guys earlier about they're really the same problem or same formula, just that the top one, again, is more specifically set up for banking, but they're the same thing. Okay, some initial amount times e to some growth rate times time equals some final amount. So we are going to use the bottom one because, again, the top one is more specifically for banking. So there's our equation. So looking back at the question, when? Okay, there's the question, when? T equals. Okay, we don't know T. So if we're going to find T, then we need to know, two words should you be saying right now? If we're going to find T, then we need to know we need two words. We're going to find T, we need to know two words. Right, Katie? Everything else. We need to find T, we need to know everything else. All right, so now we got to look through the problem, right? Where is K? Where is A sub 0 or A naught? Where is A of T? All right, where are those in the problem? Okay, how do we pull those out? So what we got? Where's K? Where's A naught? Where's T? A of T, sorry, not T, A of T. What do you see? Can you hear me, Andrew? What's up? Andrew started to tell me what K was, but then he stopped. I think it's rude. We should just finish that. Yeah, so how do we write that, though, Andrew? Yeah. What do we do with percents? We always write percents as so Andrew thinks the K is 12.3%, but he's not sure how to write it. We go from that percentage to, not quite, Victoria. What form should we always write percents in as a word? What it should always be written as what? Yeah, right, write a decimal. Okay. So how would we write 12.3% as a decimal? Zero what? That would be 1.23%. Or 50% is 0.50, right? 17% is 0.17. 3.5% is 0.035. 0.123. Okay, so we know what K is. Well, I don't see any other numbers, and we're supposed to have two more numbers. This is odd. So Andrew's seeing this double. What's that mean? How are we going to use that for? We need two numbers. So we're supposed to know everything else in order to find t, but we don't have any other numbers. We got this word double over here, but double what? I mean, doubling is something you do to something. It's not a number itself. You gotta have something to double, right? So what do we do? They didn't give us any other numbers.
Wouldn't we just like use like 1 as like the initial number and 2 as the ending number?
So you're saying that A naught should be 1, and then that since A of t would be double that would just be 2?
Yeah, because it's not asking it's asking how many years, not necessary to really have those numbers.
Okay. So can we just make up how many cases there are? Like, can she just say there's just one case and then doubling that would be 2? Is it okay just to make up the number of cases there are? Or if there's more cases, is it gonna double faster? Or double slower if there's less cases? So how do we know if this math is okay to do? Just make up a number of cases. Well, we would make up multiple sets of cases and see if it matters or not. So let's try something else. What would be a different A naught that we could try? Just give me a number. Give me a number. 26. All right, so if A naught was 26, 26 times e to the 0.123t, and doubling that would be what, 52? Okay. All right, I need another different one. Another A naught. $44. Okay. Thank you, Rhea. So what if there was 44 cases? How long would it take to double? Okay. Either way, right? What's our first step? When we go to solve these two equations, what's our first step? Divided by 44, or divided by 26, right? That's our first step, is to get rid of that coefficient, just like we just did on the last problem. Both times we do that, what does the left side become? What's 52 divided by 26? What's 88 divided by 44? 2. What's the left side? What's the right side become? E to the 0.123t. Does it matter what the initial cases is? Right? Doesn't look like it. But isn't that weird? Like, if you have 100 cases, that it would take the same amount of time to get to 200 as if you had 1,000,000 cases to get to 2 million. Doesn't it seem like it should take a lot longer to go from 1 million to 2 million than from 100 to 200? I'm guessing you probably think the same way I am. You're not saying anything. Okay? But the issue here is that people think linearly. This is not a linear problem. This is an exponential problem. We don't think exponentially very well. So it's harder for us to wrap our heads around that the change from 100 to 200 could be the same time as from 1 million to 2 million. It's because this is what's changing things, right? That exponent's what's doing that. And that means that it will act like that. So yeah, Maddie, we can do that. And so if we can pick any A naught and then thus have any A of t, what would be the easiest A naught to pick? 1. That's the easiest number to work with here. We can't pick 0. That would just kill everything. But 1, yeah, is the easiest number to pick. We get to decide. So why not pick the easiest thing? Okay. So good job, Maddie. So 2 equals 1 times e to the 0.123t. Right? So of course our first step should be to divide by 1. I know that's silly to do mathematically, but I just want to do that just because if it's something other besides 1, that still needs to be your first step, just like we just talked about. So just kind of highlighting that coefficient needs to go away first. Okay, whatever that coefficient is. But really mathematically, what we need to do here is that go logarithmic, and because it's e, just like on the last, this is really the same as the last problem we did. Natural log of 2 equals 0.123t. And then we're going to divide by the decimal there. Okay. So that's what I'm going to type in my calculator, the natural log of 2 divided by 0.123. Anytime you're doubling, this is what you would do. You would take the natural log of 2 and you would divide it by whatever the rate is. Okay, so natural log 2. You're all doing this because you know how good the practice is going to be. 5.6. Okay, 5.6 what? Right, 5.6 weeks. This is a week problem. So again, how do you report this, right? You're the health expert in the country. Your job is to go to the president or whatever and say, hey, in 5.5 weeks, we're going to be in trouble. We're going to have twice as many cases as we do right now. Okay? That's not going to be good, right? So we got to start doing what we can to bring this number down. This is the number you control, that transmission rate. Right? You start getting the PPE and better cleaning facilities and looking for medicines and stuff like that. This is what you can affect. Right? So how do we get this number to bring down? And we can't affect the cases there are right now. We find a way to get that number to come down to keep it from doubling so fast. Right? So. Right? Again, I'm choosing to say it this way. Right? 5.6 is pretty darn close to 5.5. So I'm saying about 5.5. I could say the cases will double in about 5 to 6 weeks. There's another way to say that. Cases will double in a little bit, a little more than 5 weeks. Sure. I'm giving you guys some leeway, but I want you to think about how you would say that to somebody. Using words like this, around, is helpful. Okay. You wouldn't want to say, if it was 5.9, you wouldn't want to say about 5. Be reasonable. Okay. So, I think that's super crazy that it doesn't matter the number you start with. I'm gonna skip B for right now. It's pretty much the same as that last one. So. Okay, so you guys read over that real quick. I want you to, it doesn't tell us at all what equation to use. I want you guys to read through or find the key phrase, the key words. They're going to tell us, hey, we need to go back and use this equation. Go back and look at page 101 and say, here's the equation I'm going to use because I see this word in there. I'm going to use that equation. How do we identify that? Hit me. What words in that problem are going to key you in on saying, here's the equation I should use? What you see, Caleb? What you see, Grant?
The formula I think, well, the formula I guess we use is a to the t equals p, parentheses 1 plus r, parentheses to the t power.
I heard you say a to the t. I'm guessing you're trying to say a of t?
Yeah.
Okay. So you're saying this one?
Yes.
Okay. So Grant thinks we should use that one. What told you that, Grant? What in here?
Well, I read it and it's compounding quarterly.
Okay. So you're seeing that there, and that's making you come back here?
Yeah.
Okay. You guys all good with that? Grant saw compounded quarterly. He wants to use that one. Well, Maddie says no. What do you say? What's wrong, Maddie? Did you key in on something different, or you think that means something? Or if you keyed on the same thing, do you think it's a different formula?
Quarterly is an N, like keyword,
Okay.
like yearly or like
Semi-annually.
So you would use A equals P, parentheses 1 plus R over N, parentheses NT.
What do you think about that, Grant? Is she persuading you, or you got something to counter back to her?
I'm lost. I'm not gonna lie to you.
Yeah. Do you remember using the words like quarterly and monthly and daily and stuff like that?
Yes.
Do you remember what letter they went with?
Nope.
Okay. Anybody else remember? Is Maddie remembering correctly? Those were N words? N values? I should have said N values, sorry. Anybody? Oh, you guys are really, yeah. Okay, Maddie, you're good. Yes, that is an N value there, so that would mean that N is 4, which would mean we would need a formula with N in it, which would be that one. And it says how long, right? So there's our T question again. So if we are going to find T, that means we need to know everything else, right? So we now know what N is, that's 4. What about R? What's R, Piper? Okay. And then we need to know the principal, which is the amount we put in, and we need to know the amount, which is the amount that came out. And here we are again with no more numbers in our problem. So what should we be keying in on? Triple, yeah. So just like last time, it doesn't matter if you have $1,000 and you're trying to get $3,000, or if you have $1 and you're trying to get $3. It's going to take the same amount of time because it's that growth rate that matters. It's not you're getting a penny every day. It's that you're getting just a piece of that, and the pieces will change size according to how much money you have. So, right. So if it's triple, that means you're looking at up from a 1 to 3. So we're going to use P as 1 and A is 3, or you can use P as 100 and A is 300. You can use P as 1,000 and A is 3,000. It doesn't matter what you choose. So let's just go ahead and use the smallest numbers we can. 107. All right, so there's our formula. Okay. Just like before, I guess what I really want to highlight to you guys, like if this was something different, and if those were 30 and 10, what I want to highlight to you guys is that you cannot multiply these, okay? I don't know if I'd like to tell you guys this already on the last one. I can't remember if I'm remembering something from my other class. Okay, you cannot do that. Okay, so our first step, again, just needs to be getting rid of that number. The next thing you want to do is simplify this. Okay, so plug that in your calculator. So 1.0175. Go ahead and use that whole number. You do not want to abbreviate that or approximate that right now. Okay. Never round during the middle of the problem. And I'll borrow just a minute of your time, okay? That we're going to go logarithmic. So log base 1.0175 of 3 is going to be equal to 4t. And so the next thing I would do would be to divide by 4. Okay. So as you go to find t, you do need to use change of base on this guy. So we talked about that the other day. So log of 3 divided by log of 1.0175, and then divided by 4. That's what I would type in my calculator to get my answer. So, I'll hold you any longer to make you watch and do that, but what I really need from you guys, you have the worksheet in your Google class. I need you to be looking at it. We'll finish this up on Monday, but I need you to kind of come with this is what I'm not being able to make sense of right now. So that when we are doing more examples on Monday, I can hit those things for you to get them cleared up. So, but it won't be due until Tuesday. So just kind of come ready with some questions on Monday that you've tried, even just to start the problems and see where you're getting stuck. So, all right. Have a good weekend. Be safe, Andrew.
Thank you.
See you, Ruthie. Thanks, Raya. Thanks, Grant.